Welcome to section 10.1. This is the 95th session of the CISSP exam prep series. In this session, we'll ground every other control in the building itself. We'll answer several questions. Why does physical control come before all other security? What goes into a secure facility plan? How does layered defense shape the whole design? What should drive where you put the facility? What matters most when you design the building? And how does environmental design quietly steer human behavior? Why does this matter beyond the exam? Because on the job, you inherit or influence real buildings, not just diagrams. Imagine a payment processor moving into a new campus, a research lab handling prototypes, and a regional utility running control systems. Each one lives or dies by choices made in the walls, doors, and grounds. When you are in the design room early, security becomes part of the structure. When you are not, you spend years bolting fixes onto a building that fights you. So why does physical control come before every other kind of security? Because it sits underneath all of them. If an attacker can physically reach your equipment, they can destroy it, read it, or quietly alter it, no matter how strong your logical controls are. Think of a bank with flawless account software but an unlocked backdoor to the server closet. All the encryption in the world means nothing once someone is standing at the rack. So physical protection is the foundation the rest of your program stands on. What actually goes into a secure facility plan? It is a written map of what you must protect and how you intend to do it. You build it from two inputs. A risk assessment names your assets, threats, and weak spots. Then critical path analysis traces every dependency that keeps the mission running. Picture an online store. It needs internet links, servers, power, cooling, and storage, all in a chain. Critical path analysis exposes that whole chain, so no hidden dependency surprises you later. Why should you watch out for technology convergence? Because merging systems onto one path can quietly create a single point of failure. Convergence is the drift of separate technologies into one shared solution over time. It often saves money and effort, which is why it happens. But when voice, video, building controls, and data all ride one connection, one cut can sever everything at once. That shared path also becomes a richer target. So flag convergence during design and decide where redundancy is worth the cost. How does layered defense shape the entire design? It turns the whole site into an obstacle course. A secure facility is built on overlapping layers, positioned in series rather than side by side. An intruder should have to defeat one barrier, then another, then another. Think of a medieval keep with an outer wall, a moat, an inner wall, and only then the treasure room. Each layer buys you time and raises the odds of detection. This is also why security staff belong in the design conversation from the start. Leave them out, and the building itself will undermine your logical controls. What should drive where you actually put the facility? Security needs come first, ahead of cost, size, and even location. Look hard at your neighbours, because their traffic, noise, vibrations, or hazardous materials can spill onto you. Check proximity to emergency responders, and confirm the structure can shrug off local extreme weather and resist forced entry. Study every window, door, and any tree, planter, or column that could hide someone breaking in. Then ask a strategic question. Should you be easy to find, or should you disappear? Industrial camouflage hides a facility's true purpose behind a convincing front, so a data center might wear the face of a plain food packing plant. What matters most when you design the building itself? Above everything else, protecting human life. Every design choice must satisfy the health, safety, and building code rules that apply to you, and a dedicated facility security officer can own that oversight. Beyond life safety, weigh the physical properties of walls, doors, ceilings, floors, and utility runs. Things like fire rating, load capacity, and how air and water flow through the space. Judge each element by how it could serve or sabotage your protection. A raised floor might ease cabling, or it might hide an intruder, depending on how you plan it. How can the environment itself quietly steer behavior? Through a discipline often called crime prevention through environmental design. Its core idea is simple: shape a space thoughtfully, and people behave differently inside it, so crime and even the fear of crime drop. Picture a dim alley with sunken doorways and overflowing dumpsters. Then picture a bright street with wide sidewalks and open storefronts. You feel the difference instantly, and so does a would-be intruder. Small moves reinforce this, like short planters that cannot be hidden behind, cameras mounted in plain view, few and well-watched entrances, and a data center placed at the building's core. What are the 4 principles of first-generation design? They govern the physical space directly. Access control subtly guides people to the real entrance using pathways, fences, bollards, and lighting, so the way in is obvious without shouting signs. Natural surveillance keeps sightlines open and areas well lit, so intruders always feel watched. Image and milieu use a clean, cared for, pleasant setting to signal that this place is respected and monitored. Territorial control adds flags, logos, landscaping, and clear building numbers, so outsiders feel they plainly do not belong here. What does second-generation design add on top? It shifts from the physical space to the social fabric around it. Social cohesion builds neighbors who watch out for each other and raise the alarm together. Community culture means respecting the local values and traditions, so your design fits in and earns buy-in. Connectivity creates shared paths and gathering spaces that keep eyes on the area naturally. Threshold capacity asks how much change a community can absorb before its stability frays, so new plans do not accidentally erode the very safety you want. Remember, though, none of this replaces real hardening. You still need locks, guards, fences, and bollards working alongside good design. So let's bring it together. Physical control comes first, because it underpins every other safeguard. You start with a secure facility plan built from risk assessment and critical path analysis, and you watch convergence for hidden single points of failure. You design in layers. Choose the site for security before comfort, and put life safety above all else. Then you let environmental design steer behavior across both the physical space and the surrounding community, always paired with genuine hardening. Get the building right, and every later control has solid ground to stand on. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 10.2, Part 1. This is the 96th session of the CISSP Exam Prep series. In this session, we'll start turning facility design into working controls. We'll answer several questions. How do we group physical security controls? What order should controls act in when someone tries to break in? How do you plan for equipment that will eventually fail? Why does the wiring closet deserve serious protection? What makes a server room different from an ordinary room? And how do badges and proximity devices actually decide who gets in? Why does this matter beyond the exam? Because these are the controls you specify, buy, and audit in real life. Imagine standing up a new branch office, a co-location cage, and a small clinic's records room. Each needs the right mix of policy, technology, and physical barriers, chosen on purpose. Get the mix right, and access stays controlled without slowing anyone down. Get it wrong, and you either leave doors open or grind daily work to a halt. So how do we group physical security controls into 3 familiar families? Administrative controls are the human and procedural side. Things like facility selection, site management, awareness training, and emergency procedures. Technical controls are the electronic layer, such as access systems, intrusion detection, cameras, environmental systems, and fire suppression. Physical controls are the tangible barriers, like fences, lighting, locks, and guards. Notice the label physical is a bit narrow, since real facility protection blends all 3. Think of a vault. The rules for who may enter, the electronic lock, and the steel door itself each play a distinct part. What order should controls act in when someone tries to break in? There is a functional sequence worth memorizing: deter, deny, detect, delay, determine, and decide. First, you deter with visible boundaries that discourage the attempt. If that fails, you deny direct access, say with a locked vault door. If they get past that, you detect the intrusion with sensors. Then you delay them long enough for help to arrive, perhaps with a cable lock tethering the asset. Finally, staff determine what is actually happening and decide how to respond, whether that means detaining the intruder or preserving evidence. A cable lock will not stop a determined thief, but the obvious damage from cutting it makes the stolen device hard to sell. How do you plan for equipment that will eventually fail? By matching your preparation to how critical the asset is. For low-stakes gear, knowing where to buy a replacement within a couple of days may be enough. For critical systems, you keep spare parts on site, accepting that faster recovery costs more in storage and expertise. When on-site spares are not practical, you sign a service-level agreement with the vendor that pins down exactly how fast they will respond. You also plan around 3 lifetime numbers. Mean time to failure is how long a device typically lasts, so replace it before that point. Mean time to repair is how long a fix takes. And mean time between failures tracks the gap between repeated failures. Above all, always have a backup unit ready, because waiting for total failure before replacing anything is simply unacceptable. Why does the wiring closet deserve serious protection? Because it is the nervous system of the building's network. A cable plant is the whole web of cables and gear that forms the physical network, from the entrance facility where the provider's line arrives, through the equipment room, the backbone, the wiring closets, and the horizontal runs to each work area. To guard the cables themselves, a protected distribution system uses sealed conduits, tamper-evident connections, and regular inspections to deter, detect, and prevent compromise. These closets also often hold alarm panels, breakers, and camera feeds, so an intruder who reaches one could steal gear, cut lines, or plant a listening device. So lock it tight, keep it clean and clutter-free, never treat it as a storage room, log every entry, restrict keys to the administrator, and inspect it on a schedule. What makes a server room different from an ordinary room? It is built for the equipment, not for people. A server room is a restricted, enclosed space, often run lights out and kept cool, because comfort for workers is not the goal. It may include gas-based fire suppression and walls rated to resist fire for a set period. Place it at the core of the building and avoid the ground floor, top floor, and basement, along with anywhere near water, gas, or sewage lines that could leak or flood. Some organizations run their own room, while others lease space from a co-location or cloud provider in single-tenant or shared arrangements. Either way, physical access is managed with layered technical controls, from smart cards and proximity readers to biometrics and intrusion detection tuned for people, not packets. How do badges actually decide who gets in? By carrying either identity, authentication, or both. A badge can be as plain as a name tag marking employee or visitor, or as capable as a smart card using multi-factor authentication. A smart card is a credit card-sized token with an embedded chip that can hold or even process data, and it represents something you have. Because a single factor is never enough, it is usually paired with a personal identification number, so a stolen card alone will not let someone impersonate you. A magnetic stripe card is weaker, since it only stores data and is easy to copy, so it should not stand alone in a secure setting. And remember the distinction. Used for identification, the badge is swiped and then a second factor is required. Used for authentication, the person presents an identity first and swipes the badge to prove it. When staff leave, collect and destroy their badges as part of offboarding. How do proximity devices decide who gets in? By quietly signaling to a nearby reader who the bearer is. The device is worn or carried, and when it passes the reader confirms identity and access rights. There are 3 flavors. A passive device has no electronics of its own, just a small magnet that alters the reader's electromagnetic field, much like the anti-theft tags on store merchandise. A field-powered device wakes up and draws its power from that same field, which is the everyday card you wave inches from a door. A transponder is self-powered and actively transmits its signal, either continuously or when you press a button, like a garage remote or a car key fob. A related feature, automatic request to exit, uses motion sensors or pressure mats to unlock a door automatically as someone approaches from inside, easing exits without weakening entry control. So let's bring it together. Physical security controls fall into administrative, technical, and physical families, and they should act in the order: deter, deny, detect, delay, determine, and decide. You prepare for inevitable equipment failure with spares, vendor agreements, and lifetime metrics. You harden the wiring closet as the network's nervous system, and you build the server room for equipment at the building's core. And you control who enters using badges, smart cards, and proximity devices, always layering more than one factor. Master these building blocks, and the rest of your physical program clicks into place. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 10.2, Part 2. This is the 97th session of the CISSP Exam Prep series. This part carries the same facility controls forward into detection, alarms, and recording. In this session, we'll focus on catching intruders in the act. We'll answer several questions. What is a physical intrusion detection system, and how can it be defeated? How do motion detectors sense someone moving? How do you know when a perimeter is crossed? What does an alarm actually do once it triggers? How do you cut down on false alarms? What role do cameras really play? How do people abuse physical access? And how do you store media so it stays safe? Why does this matter beyond the exam? Because detection is where physical security earns its keep. Picture a distribution warehouse, a boutique bank branch, and a media production studio holding unreleased footage. Each one needs to know the instant something is wrong and to have a clean record afterward. When your detection is layered and your logs are solid, you respond fast and reconstruct events with confidence. When it is thin, you find out too late and cannot prove what happened. So what is a physical intrusion detection system, and how can it be defeated? It is a system, automated or staffed, that spots an unauthorized entry or an event happening at the wrong time. In physical form, these are burglar alarms, often using a simple contact switch that senses when a door or window opens, plus foil strips or wire grids that catch broken glass. But two weak points can silence one. If it loses power, it stops working, so a reliable system carries a battery backup good for at least a full day. And if its communication line is cut, no one gets notified. So it uses a heartbeat sensor that constantly checks the pathway and trips the alarm the moment that signal drops. Together, those defeat an intruder who tries to cut the power or the wires. How do motion detectors sense someone moving? Each type watches a different physical signal, and you pick the one that fits the space. A digital detector flags meaningful changes in a camera-like image. A passive infrared type reads shifts in heat. A wave pattern or microwave detector bounces a signal and watches the reflection for disturbance. A capacitance detector senses changes in the electromagnetic field around an object. A photoelectric detector notices changes in light, so it suits windowless rooms kept dark. And a passive audio detector simply listens for abnormal sounds. To cut false alarms, a dual technology sensor combines two of these, usually infrared and microwave, and only reacts when both agree. How do you know when a perimeter is crossed? With sensors placed right at the boundary, a contact device detects a door or window opening, often using a balanced magnetic switch, two small units on the frame and the door that hold a circuit until the magnet pulls far enough away to break it. Wire that straight to an alarm, and the instant the door opens, it sounds. An infrared linear beam sensor projects a beam across an opening, and when a person walks through and blocks it, the brake registers. Think of the safety beam at the bottom of a garage door that stops it from closing on a bag. Cross that invisible line, and the system knows. What does an alarm actually do once it triggers? It launches one of three kinds of response. A deterrent alarm makes further intrusion harder, engaging extra locks or closing doors. A repellent alarm drives the intruder off, blaring a siren and flooding the area with light. A notification alarm stays silent to the intruder but records the event and quietly summons administrators, guards, or police, hoping to catch them in the act. Alarms are also grouped by where the response lives. A local system sounds on site and needs guards nearby to react. A central station system is monitored off-site by a firm that responds for you. and an auxiliary system loops in emergency services like fire, police, or medical. You can blend these into one solution. How do you cut down on false alarms? By demanding a second opinion before you trust the first. The more sensitive a sensor, the more often harmless things set it off. Animals, birds, blowing trash, or even authorized staff. So you deploy 2 or more detection systems and require several to trigger together in quick succession before an alarm is raised. Cameras play into this too, but a camera is not an automatic responder. Someone has to watch the feed, unless it has smart detection built in. So a visible camera works as a deterrent, while reviewing its footage after a trigger works as detection, exactly like an audit trail. Pair a primary sensor with a camera, and you confirm real threats without chasing every shadow. What role do cameras really play? They deter unwanted behavior and create a lasting record. Position them at entries, exits, hallways, and around valuable assets with clear sight lines. Make them overt to warn people off, or hide them to quietly capture wrongdoing. Cameras vary widely, some fixed, some offering remote pan, tilt, and zoom, and many recording to local or cloud storage in visible or infrared light. Advanced units run their own processing for facial recognition, object detection, or time-lapse, and some even track movement or read gait, the unique way a person walks, as a biometric. But smart cameras can be fooled by weather or wildlife, and being network connected, they can be attacked or hijacked, so back them with a secondary check. How do people abuse physical access? Usually by exploiting trust or a propped open door. Common abuses include wedging a secured door open, bypassing a lock, or using someone else's credential to impersonate a valid person. Tailgating and piggybacking mean slipping in behind an authorized employee, either without their notice or with their misguided courtesy. The defense is watchful people and solid records. Audit trails and access logs, whether captured by a guard's pen or automatically by smart cards, let you see who requested entry, whether they were authenticated, and how long a door stayed open. Tie those logs to camera footage, and you can reconstruct exactly what happened during an incident. How do you store media so it stays safe? By protecting it against theft, corruption, and leftover data. A media storage facility holds blank, reusable, and installation media, all locked away rather than left on an open shelf. Blank media must be secured so no one steals it or slips malware onto it before use. Reusable media is riskier because standard deletion only marks space as free and leaves the original bits recoverable by a simple undelete tool. Those leftover bits are data remnants, and you erase them with secure wiping or zeroization, then verify with a hash check. Put a librarian in charge, track everything with a check-in and check-out process, and know the difference between a safe, a movable strongbox, and a vault, which is built permanently into the structure. So let's bring it together. A physical intrusion detection system spots unauthorized entry, and you shield it against power and line attacks with battery backup and a heartbeat sensor. Motion detectors sense heat, light, sound, waves, or fields, while perimeter sensors catch a door opening or a beam breaking. Alarms deter, repel, or notify, and you fight false positives by requiring multiple triggers and backing sensors with cameras. Cameras deter and record, but they need a human or a secondary check. Watch for access abuses through solid logs, and store media locked, tracked, and fully wiped. Layer all of this, and nothing crosses your boundary unseen. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 10.2, Part 3. This is the 98th session of the CISSP Exam Prep series. This part moves from detection into evidence, work areas, and the utilities that keep everything running. In this session, we'll protect the environment that surrounds your equipment. We'll answer several questions. How do you store digital evidence so it holds up? How do you design work areas by sensitivity? Why is clean, steady power such a big deal? What power problems should you be able to name? How does electrical noise creep into your systems? And how do you keep temperature and humidity in a safe range? Why does this matter beyond the exam? Because the unglamorous utilities are what quietly keep the business alive. Think of a law firm preserving case evidence, a trading floor that cannot tolerate a flicker, and a manufacturer whose shop floor servers bake in summer heat. Each one fails in a different way if you ignore power, cooling, or evidence handling. When you get these fundamentals right, systems stay up and investigations stay defensible. When you skip them, you lose data, uptime, and sometimes the case itself. So, how do you store digital evidence so it holds up? By keeping it isolated, tracked, and provably unchanged. Evidence storage is no longer just a police concern, because every organization now gathers logs, drive images, and machine snapshots for investigations. Keep that data on a dedicated system, separate from your production network, and take it offline when you are not actively adding to it. Block internet access to and from it. Log every action taken on it, and limit access to your security administrator and legal counsel. Encrypt everything stored there, and calculate a hash for each dataset, so you can later prove nothing was altered. That chain of care is what makes evidence usable in an internal case or a courtroom. How do you design work areas by sensitivity? By thinking in concentric circles of protection. Not every space deserves equal access, so the more valuable the assets inside, the harder that area should be to reach. Anyone can find the restroom, but only administrators reach the server room with the most sensitive assets sitting at the protected center. Separate distinct work zones with real walls. And where secrecy matters, run them floor to ceiling, cutting through any suspended ceiling so no gap becomes a crawl through. A clean desk policy locks away sensitive papers at the end of each shift, shrinking the chance of casual disclosure. Classify each area like you classify data, control visitors with escorts and logs, and for the highest tier, a sensitive compartmented information facility gives government-grade isolation, often banning cameras and phones inside. Why is clean, steady power such a big deal? Because the electricity from the wall is neither as clean nor as constant as your gear needs. You defend it in escalating levels. A surge protector is the bottom rung, guarding only against overloads, and it cuts power entirely when its fuse blows. A power conditioner does more, filtering out line noise as well. An uninterruptible power supply climbs higher, using a self-charging battery to deliver clean, conditioned power and to carry the load briefly when the grid drops. A double conversion type always runs power through its battery for a seamless feed, while a line interactive type switches to battery only when the grid fails, sometimes with a tiny gap. For whole building coverage, there are large failover batteries, and at the top sit generators, which start automatically and with enough fuel run for a long time. Keep the battery even with the generator, since it bridges the minutes before the generator warms up. What power problems should you be able to name? A precise vocabulary, because the fix depends on the fault. A fault is a momentary complete loss, while a blackout is a prolonged one. A sag is a brief drop in voltage, and a brownout is a prolonged one. A spike is a momentary surge of high voltage, while a surge is a sustained one. An inrush is the initial jolt when equipment first connects to power, and ground is the safe return path that lets electricity flow harmlessly to the earth. One more practical rule: if the trouble starts outside your meter, it belongs to the utility, but anything inside is yours to fix. How does electrical noise creep into your systems? As interference riding along on the power or through the air, noise is any disturbance in the power supply. And when it comes and goes, it is called transient noise. Electromagnetic interference is generated by electric current and can corrupt transmissions on phone, network, and radio links. Radio frequency interference comes from everyday devices like fluorescent lights, motors, elevators, and space heaters, and it disrupts many of the same systems. You fight both by conditioning the power, grounding properly, using shielded cables and conduits, and switching sensitive links to fiber, which simply does not care about electromagnetic noise. Locate the noisy equipment first, then route your cabling to stay clear of it. How do you keep temperature and humidity in a safe range? By steady control, not just cold air. Equipment rooms generally sit between about 59 and 90 degrees Fahrenheit, but stability matters more than any exact number because swings expand and contract components. That oscillation causes chip creep, where seated chips slowly walk out of their sockets and can crack solder joints. In big rooms, hot and cold aisles line up racks so intake vents pull cool air in and capture the hot exhaust, keeping the flow organized. Humidity stays roughly between 20 and 80%. Too much invites condensation and corrosion, while too little lets static build until an electrostatic discharge from your fingertip fries a circuit. Add positive air pressure and good filtration to keep dust out. Watch for plenum-rated cabling in airspaces, and use environmental and condition monitoring to catch trouble before it becomes an outage. So let's bring it together. Store evidence on an isolated, offline, encrypted system with tracked activity and per dataset hashes, so it stays defensible. Design work areas as concentric circles, using solid walls, clean desks, classification, and escorts, with a sensitive compartmented information facility at the top. Protect power in levels, from surge protectors up through conditioners, uninterruptible supplies, and generators, and learn the vocabulary of faults, sags, and surges. Shield against electromagnetic and radio noise, and hold temperature and humidity steady to stop chip creep, corrosion, and static. Nail these utilities, and your equipment runs clean, cool, and continuously. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 10.2, Part 4. This is the 99th session of the CISSP Exam Prep series. This part closes out facility controls with water, fire, and life safety. In this session, we'll defend against the two great physical threats, water and fire. We'll answer several questions. Why is water such a danger to your systems? What is the fire triangle? And how do the stages unfold? Why does fire training come before any technology? Which fire extinguisher fits which fire? How do automated systems detect a fire? How do water suppression systems differ? When do you reach for gas instead of water? And what damage lingers even after the flames are out? Why does this matter beyond the exam? Because when water or fire hits, people's lives come first, and the wrong response makes things worse. Picture a basement data closet under old plumbing, an office kitchen next to a server rack, and a remote generator shed full of fuel. Each carries a specific hazard that demands a specific control. When you plan for these deliberately, you protect staff and limit damage. When you improvise, you risk lives, equipment, and the business itself. So why is water such a danger to your systems? Because water and electricity together mean destroyed gear and a real risk of electrocution. Leaks are rare, but when they happen, the damage is severe. So locate server rooms and critical equipment well away from pipes and water sources. Install water detection circuits on the floor or beneath a raised floor, so an alarm sounds the moment moisture creeps toward the racks. Know where your shut-off valves and drains are before you ever need them. And look at the bigger picture. Is the building on a hill or in a valley? Does it drain well? And has the area flooded before? Answer those questions before you commit to a location. What is the fire triangle? And how do the stages unfold? The triangle names the three ingredients every fire needs: fuel, heat, and oxygen, feeding a chemical reaction at the center. Remove any one, and the fire dies, which is exactly how each suppressant works. Water pulls out heat, dry powders and soda acids smother the fuel, carbon dioxide displaces the oxygen, halon substitutes disrupt the chemistry, and film-forming foam attacks both heat and fuel. Fire also moves through 4 stages. First, the incipient stage, only ionized air and no smoke. Then the smoke stage, visible smoke. Then the flame stage, visible fire. And finally, the heat stage, intense and consuming. Catch it early, and both the fire and the cleanup stay small. Why does fire training come before any technology? Because no sprinkler saves a life the way preparation does, and protecting people is always the top goal. Train everyone on escape procedures and make sure each person knows at least 2 evacuation routes from their area. Post maps, mark exits clearly, and set a rendezvous point so you can confirm everyone got out. Teach staff where extinguishers are and how to use them, and fold in basics like first aid, resuscitation, and the automated defibrillator. Then test it all with regular drills, because a plan no one has practiced fails under real pressure. In many places, inspecting alarms, detectors, and extinguishers on a schedule is not optional, it is the law. Which fire extinguisher fits which fire? The class has to match the fuel, or you make things worse. Class A handles ordinary combustibles like paper and wood, put out with water or soda, acid. Class B is for flammable liquids, which need foam or gas. Never water, since water would spread the burning liquid and cause an explosion. Class C covers electrical fires, where you use carbon dioxide or a gas, because water risks electrocution. Class D is for burning metals, which make their own oxygen, so only dry powder works. And Class K is for cooking oils and fats, quenched with alkaline agents. Most offices carry a multi-class ABC extinguisher, and remember, any extinguisher is useless once the fire reaches that final heat stage. How do automated systems detect a fire? Each type keys off a different sign of combustion. A fixed temperature detector, the common sprinkler head, triggers when a set temperature melts or shatters its element. A rate of rise detector reacts to how fast the temperature climbs, though winter heating can fool it. A flame-actuated detector senses the infrared signature of flames, fast and reliable but pricey, so it guards high-risk spaces. A smoke-actuated detector watches for particles blocking light or ionized air across a gap. And an incipient or aspirating detector sniffs out the chemistry of combustion before anything is even visible, the earliest warning and the most expensive. Whatever you choose, place detectors everywhere, including drop ceilings, raised floors, ducts, and shafts. How do water suppression systems differ? By how and when they let the water flow. A wet pipe system stays full and discharges instantly. Simple but risky, where a leak would ruin equipment. The dry pipe system holds pressurized gas that, once released, opens a valve so water fills in moments later. A pre-action system adds a 2-stage safeguard, filling the pipes only after early fire signs appear and releasing water only after the sprinkler head itself triggers, which lets you halt a false alarm before a drop falls. And a deluge system dumps a huge volume through wide-open heads all at once, which is entirely wrong for rooms full of electronics. For a space with both people and computers, the pre-action system is the safe choice, because it gives you a chance to stop a mistake. When do you reach for gas instead of water? When people are not present and water would do harm. Gas systems smother fire fast and leave equipment undamaged, but they work by removing oxygen, which makes them deadly to anyone in the room. Carbon dioxide is effective, yet dangerous, since even a modest concentration can asphyxiate, and it is colourless and odourless, so it gives no warning. Halon starves the fire by breaking the combustion chemistry, but it harms the ozone layer and turns toxic at high heat. So it has been phased out in favour of cleaner substitutes like FM200. Reserve gas systems for spaces without people, like engine compartments, generator rooms, and areas around flammable liquids. What damage lingers even after the flames are out? More than you might expect, because the fire is only part of the harm. Smoke and soot ruin storage devices and components, heat warps and cracks hardware, and even modest temperatures can destroy tapes and data. The suppression itself adds insult, as water and chemicals cause short circuits and corrosion. And do not forget the responders, whose hoses and axes tear through a space as they search for people and hotspots. Any fire, even a small one, may set your incident response, business continuity, and disaster recovery plans into motion. Plan the full aftermath, not just the blaze. So let's bring it together. Water and electricity never mix, so keep systems away from pipes, add detection circuits, and study the site for flooding. Fire needs fuel, heat, and oxygen, and every suppressant removes one, while the 4 stages reward catching it early. Life safety and trained, drilled people come before any technology. Match the extinguisher class to the fuel, pick detectors and suppression to fit the space, and choose gas only where no one breathes. And plan for the lingering damage from smoke, heat, suppressant, and rescue. Do this well, and the worst physical events stay survivable. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 10.3, Part 1. This is the 100th session of the CISSP Exam Prep series. In this session, we'll build the outer defences of a facility from the fence line inward. We'll answer several questions. What quiet role does signage play? Why does the perimeter shape accessibility? How do fences, gates, turnstiles, and person traps stop intruders? What does lighting really accomplish? Why do guards and dogs still matter in an automated world? And how do you handle visitors once they are inside? Why does this matter beyond the exam? Because the perimeter is where most attacks are either discouraged or invited in. Imagine a suburban corporate campus, a downtown data center on a busy street, and a rural warehouse beside a highway. Each one needs a boundary tuned to its surroundings and its threat level. When you design that boundary thoughtfully, most trouble never reaches the front door. When you neglect it, you are defending the lobby instead of the property line. So, what quiet role does signage play? It sets expectations and quietly shapes behaviour before anyone touches a lock. Signs mark areas as off-limits, announce that cameras are watching, point out entrances and exits, and post safety warnings. They deter petty wrongdoing, guide honest people into compliance, and establish a basis for holding rule breakers accountable. And signage is not only physical. Digital warning banners belong on your local and remote connections too, telling anyone who logs in exactly where the boundaries lie. Think of a plainly posted no entry sign at a restricted door. It rarely stops a determined intruder, but it removes any honest excuse. And remember to test every physical control on a schedule, even when no regulation forces you to. Why does the perimeter shape accessibility? Because security and access are always in tension, and you have to balance them on purpose. A single entrance is easiest to secure, but multiple exits are safer when people must evacuate fast. Nearby roads, transit, and daily traffic all affect how exposed you are and how quickly help arrives. The point is that convenience cannot run free. It has to bend to support your perimeter. So you channel people and vehicles through control points, monitor everyone entering and leaving, and log every physical event. Design the boundary first, then let accessibility fit within it. How do fences, gates, turnstiles, and person traps stop intruders? By forming a layered physical boundary, each piece tuned to a threat. A fence defines the line, and its height signals its purpose. A low fence deters a casual wanderer. A taller one turns back most people, and an 8-foot fence topped with razor wire stops all but the determined. For high security sites, a perimeter intrusion detection and assessment system uses 2 or 3 fences together, with an outer fence keeping animals away from the sensitive inner one and reducing false alarms. A gate is the controlled opening, and it must be as strong as the fence around it, or it becomes the weak link. A turnstile lets just one authenticated person through at a time, like a secure revolving door. A person trap, also called a man trap or access control vestibule, holds someone between 2 doors until their identity is verified, then either admits them or locks them in for an escort. Add bollards to stop vehicles from ramming an entrance, and barricades like planters and zigzag queues to control the flow of people and cars. What does lighting really accomplish? It discourages the casual intruder who would rather work in the dark. Lighting is the most commonly deployed perimeter control, and its whole value is deterrence, especially around parking, walkways, and entrances. Run exterior lights from dusk to dawn, and add emergency lighting on exits and escape routes that kicks in when power fails or a fire alarm sounds. But lighting is a weak deterrent on its own, so pair it with cameras, guards, or sensors. Aim it carefully, too. Poorly placed lights create glare that blinds your own guards and cameras, and a bright light on a fence line pointed inward can actually hide an intruder standing in front of it. Space the poles so the pools of light overlap, leaving no dark gaps for someone to slip through. Why do guards and dogs still matter in an automated world? Because a human can judge a situation in a way no sensor can. Every static control ultimately relies on a person to intervene, and guards bring adaptability, recognizing new attack patterns and making decisions on the spot. Send them on frequent patrols, but at random times, so an intruder cannot learn the schedule and time of break-in. Guards are not perfect, though. They can be unreliable, get sick, take vacations, fall for social engineering, and they are expensive, whether staff or contracted. Interestingly, their limited knowledge of your operations is a quiet benefit, since they cannot leak what they do not know. Guard dogs are an effective deterrent and detector, but costly to house, feed, and insure. And robot sentries, on wheels or as drones, can now patrol automatically, often using facial recognition to spot intruders. How do you handle visitors once they are inside? By controlling and tracking them from the moment they arrive. If your facility has restricted areas, you need a real process for outsiders, usually an assigned escort who monitors their access and activity closely. Fail to track visitors, and you invite malicious activity against your most protected assets. Reception works as a choke point, segregated from secure areas behind locked doors and watched by cameras. There, an authorized visitor gets an escort, a known worker gets buzzed in, and anyone unauthorized is turned away or handed to security. Keep visitor logs, whether written by a guard or captured automatically, because those physical records give context to your digital logs and help confirm everyone got out safely in an emergency. So let's bring it together. Signage sets expectations and quietly deters, while the perimeter forces a deliberate balance between security and access. Fences, gates, turnstiles, and person traps build a layered boundary, backed by bollards and barricades against vehicles. Lighting deters the casual intruder, but only when aimed well and paired with other controls. Guards and dogs add human judgment that sensors cannot match, and robot sentries extend their reach. And once visitors are inside, escorts, choke points, and logs keep them accounted for. Build the outer layers well, and threats lose steam long before they reach anything valuable. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 10.3, Part 2. This is the 101st session of the CISSP Exam Prep series. This part moves from the perimeter inward to locks, life safety, and how you measure it all. In this session, we'll finish physical security with the details that keep it honest. We'll answer several questions. How do locks really control access, and how do they fail? Why does life safety outrank everything else? How do regulations set your baseline? And how do you actually measure whether physical security is working? Why does this matter beyond the exam? Because these are the pieces that turn a security program from good intentions into something you can prove. Picture a clinic securing a drug cabinet, a factory meeting strict safety law, and a retailer reporting break-in trends to its board. Each depends on solid locks, legal compliance, and honest measurement. When you get these right, you protect people, satisfy regulators, and show leadership real numbers. When you skip them, you are guessing, and guessing does not hold up in an audit or a courtroom. So how do locks really control access, and how do they fail? A lock is a crude but effective gatekeeper. If you hold the right key, or combination, it treats you as authorized, which makes it a basic form of identification and authorization. Ordinary key-based locks, the preset and deadbolt kind, are cheap and common, but they fall to picking a broader class of attacks called shimming, and to bumping, where a special key is tapped to jolt the pins loose. Programmable and combination locks offer more control, supporting multiple codes or electronic keypads and card readers. An electronic access control lock combines three parts: an electromagnet holding the door shut, a reader that authenticates you and releases the magnet, and a sensor that relocks once the door closes. Such a lock can even warn when a door lingers open too long, or raise an alarm if it stays open longer still. Why does life safety outrank everything else? Because protecting people is the single most important goal of every security control, without exception. People can survive briefly without water, power, or cooling. But losing those can signal a far more dangerous problem unfolding. Floods, fires, toxic releases, and disasters, both natural and human-made, all threaten lives before they threaten equipment. So your procedures put human safety first, then restore a safe environment, then bring the IT infrastructure back. Many organizations adopt an occupant emergency plan for exactly this, guiding how to minimize danger, prevent injury, and protect property during a destructive event. Keep the roles clear, though. That plan covers people and property, while the business continuity plan and disaster recovery plan handle IT and business recovery. People come first, and only once they are safe do you turn to keeping the business running. How do regulations set your baseline? By defining the floor you must build on, not the ceiling you aspire to. Every organization lives inside an industry and a jurisdiction, and often a state and city on top of that, each imposing its own legal requirements. Those rules touch software licensing, hiring limits, handling of sensitive materials, and safety compliance. Meeting all of them is a core part of sustaining security, and you treat that legal baseline as the foundation for everything else you add. Think of it as the minimum bar. You are never done at compliance, but you are never secure below it either. How do you actually measure whether physical security is working? Through key performance indicators, the metrics that reveal what is succeeding and what is failing. These measurements let management make informed decisions and steer toward better protection at a sensible cost, since the whole point of security is reducing risk affordably. Track things like the number of successful and unsuccessful intrusions, crimes, and disruptions, along with how long it takes to detect, assess, respond to, and recover from an incident, plus the rate of false alarms. Set a baseline for each, and record every reading, because only a history lets you spot trends. Automated collection is more reliable, while manual readings often matter more but demand real attention. Close every incident with a lessons learned step that captures fresh data, and use it all to run return on security, investment, and cost-benefit analysis on your controls. So let's bring it together. Locks are crude gatekeepers, cheap keyed ones vulnerable to picking and bumping, while electronic access control adds a reader, a magnet, and a sensor for real oversight. Life safety outranks everything, so procedures protect people first, restore the environment next, and recover IT last, with an occupant emergency plan separate from your continuity and recovery plans. Regulations set the baseline you must never fall below, and key performance indicators, tracked against a baseline over time, turn physical security into something you can measure, defend, and justify. Master these final pieces, and your physical program stands on solid, provable ground. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.